So, imagine paying £1,500 for a piece of cutting-edge technology today.
Right. That's what, high-end laptop territory.
Exactly, like flagship tablet or laptop money. You bring this incredibly expensive machine home, you carefully plug it into the wall, hook it up to your computer, and ask it to perform one single basic task. And then you just wait.
I didn't wait.
Yeah, you wait 12 agonizing, incredibly noisy minutes for it to finish.
Which is wild to think about.
I mean, in our modern era, you'd assume the machine was completely broken, right? You'd be on the phone with customer support, immediately demanding a refund.
Oh, absolutely.
But, in 1984, people didn't just tolerate that 12-minute wait. They actually celebrated it. They looked at that machine and considered it an absolute triumph of modern engineering.
It sounds like a paradox, honestly, but it is entirely true. And, to understand why a 12-minute wait for a single document was seen as this huge breakthrough, we really have to strip away all of our modern biases.
Which is hard to do.
It really is. Today, we expect our technology to have this kind of seamless invisibility. You tap a piece of glass on your phone, a silent radio wave flies through the air, and somewhere across the house, a laser silently fuses microscopic toner to a crisp white page.
And it happens in seconds.
Right. It's totally frictionless.
It is basically magic. But, it's also a very passive experience for the user. We like our tools to get out of our way now.
Definitely. We want the complexity hidden.
Yeah, behind these sleek, glued-together aluminum enclosures. And that is the exact opposite of the world we're stepping into today. So, welcome to the Deep Dive. Today, our mission is to take you back to a very specific, unapologetically mechanical snapshot in technological history.
A very loud snapshot.
Oh, very loud. We're looking at an era where users weren't just passive consumers, they were mechanics. They were hardware troubleshooters.
Software hackers, even.
Exactly. And patience was just a mandatory requirement.
So, the foundation for our exploration today is this really brilliant piece of vintage tech journalism. We've been analyzing a deeply detailed review from the December 1984 issue of Personal Computer World magazine.
Such a great source.
It really is. And the focus of the review is a specific peripheral that perfectly encapsulates this whole era. It's the Juki 6100 Daisywheel Printer.
The Juki 6100.
Yeah. And looking at this machine, it forces us to reevaluate the relationship between the human and the computer. It highlights exactly what we prioritized back then and, maybe more importantly, what we've lost in our current age of these sealed, unrepairable devices.
Okay, so let's unpack this, because the raw numbers we're dealing with here are just going to blow your mind. I mentioned that £1,500 price tag earlier.
Yeah.
The actual 1984 list price for the Juki 6100 was £370. But we ran that through the inflation calculators to bring it into a 2026 context, and it comes out to a staggering £1,543.75.
For a printer.
For a printer. And here's the absolute kicker. The magazine review constantly refers to this as an inexpensive budget price.
Wow.
Yeah, it was celebrated for being cheap.
Which really tells you everything you need to know about the state of the market in the mid-1980s.
Right. So I have to ask the obvious question here. If I'm a consumer, and I'm spending the modern equivalent of a high-end laptop on a printer, and it takes 12 minutes to print a standard 2,000-word article, why did this thing even need to exist?
That's the big question.
I mean, surely there were faster ways to get words onto paper in 1984.
There absolutely were. But to understand why the Juki 6100 existed, you have to understand the deeply fractured nature of the early consumer hardware market.
Okay.
If you were setting up a PC system for your home, or, your small business, you essentially had to walk down one of two very different, mutually exclusive paths.
Like a fork in the road.
Exactly. It was a stark binary choice dictated by pure physics and economics. You either chose speed or you chose print quality.
But not both.
You absolutely could not have both. Unless, of course, you were a massive corporation willing to spend the equivalent of a small car on an early commercial laser printer.
So let's walk down that first path, the path of speed. If I'm a consumer in 1984 and I want my documents printed fast, what am I buying?
You're buying a dot matrix printer. And the heavyweight champion of that category, the one the magazine review constantly uses as a baseline comparison, was the Epson FX80.
Okay, I've seen old dot matrix printouts in archives. They look a lot like grocery store receipts.
That's a perfect comparison.
But I'm not entirely sure how the underlying physics worked. Like, how did they achieve that speed?
It was all about minimizing physical movement. So the print head of a dot matrix printer was incredibly light. Inside that head was a vertical column of tiny needle-like metal pins.
Okay, just little pins.
Right, and behind each pin was a tiny electromagnet. So as a motor zipped the print head horizontally across the paper, the computer would rapidly pulse electricity into those electromagnets.
So it's firing as it moves.
Exactly. The magnets would fire the pins outward, striking an inked ribbon against the paper. By selectively firing different combinations of pins as the head moved, it formed characters out of a grid of tiny dots.
Zip, 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 right across the cage.
Very fast, very loud.
And the speed on that Epson FX80 was what exactly?
In its standard draft mode, it could hit an incredibly impressive 100 characters per second.
100 characters per second. Okay,
Yeah.
so at that speed, a 2,000-word article, which is, roughly a standard university essay or a long business memo, that would only take about 2.5 minutes to print.
Right.
That's practically modern speed. I mean, why wouldn't everyone just buy the Epson?
Because of the output quality. You hit the nail on the head earlier when you said it looked like a grocery receipt. The text was jagged. It was heavily pixelated.
Oh, right, because of the pins?
Exactly. You could literally see the individual round dots making up the curves of a letter O or an S. There were actual gaps between the dots. It fundamentally looked like a computer had printed it.
And I'm guessing in 1984, looking like a computer printed your document wasn't exactly a badge of honor.
Oh, it was a massive professional liability.
Really?
Oh, yeah.
Yeah.
We have to remember the social and economic context of the era. The physical letter was the primary medium of formal business communication.
Because there's no email.
Right. There are no attached PDFs. If you are a law firm sending a contract, or an architecture firm submitting a proposal, or, an author sending a manuscript to a publisher, the physical piece of paper is your final product. It completely represents you.
So if your proposal arrives on a client's desk looking like a pixelated, jagged mess, it subtly communicates that you're cutting corners.
It looks cheap. It looks mass-produced.
Ah, I see.
It lacked the gravitas, the physical authority of a traditional typed document. Business culture really dictated that formal correspondence must look like it was typed by a professional human on a high-end electric typewriter. Yeah, that crisp, solid, dark lettering was just non-negotiable for serious work. Now, the Epson FX80 did have a slower, so-called correspondence quality mode, where the print head would do a double strike.
Like going over it twice.
Yeah, shifting slightly to fill in the gaps between the dots, but it still couldn't perfectly replicate the solid strike of a typewriter.
Which brings us to the second path, the path of quality. And this is where our Juki 6100 enters the picture. It belongs to a family of machines called Daisywheel printers.
Yes.
Even the name sounds completely foreign to modern ears. What exactly is a daisy wheel?
It's essentially a mechanized automated typewriter. Instead of a grid of pins forming dots on the fly, the printer relies on a physical, interchangeable wheel. It could be made of plastic or metal.
Okay.
Imagine a central hub with dozens of little flat spokes radiating outward. It looks almost exactly like the petals of a daisy flower, which is where the name comes from.
Okay, I'm picturing it. Like a flower made of plastic.
At the very end of each petal is a fully formed, raised physical character. A capital A, a lowercase b, a comma, a number.
Oh, wow.
It's the exact same concept as the metal letter blocks on a vintage manual typewriter, just arranged in a flat circle.
Let me see if I have the mechanics right here. To print a single letter, the machine has to physically spin this entire wheel until the correct character petal is perfectly aligned with the paper.
Yes.
And then what? A hammer hits it.
Precisely. A tiny electromagnetically driven mechanical hammer fires from behind the wheel. It smashes into the back of that specific petal, bending it forward just enough to strike the inked ribbon and press the solid letter form against the paper.
So, because it's using a solid pre-molded character, the output must be absolutely flawless.
It was absolute aesthetic perfection for the era. They called it letter quality. Unless you looked at it under a microscope, the output was indistinguishable from a high-end professional office typewriter.
That's incredible.
The letters were crisp, the ink transfer was solid, the curves were perfectly smooth.
But the trade-off for that perfection is the speed. And this brings us back to that agonizing 12-minute wait. The math of impatience here is just staggering.
It really is.
We said the dot matrix was hitting 100 characters per second. What was the Juki 6100 doing?
18?
Wait, just 18.
18 characters per second.
That is a monumental drop in performance. You're going from a sports car to a bicycle.
You really have to consider the incredible mechanical overhead happening for every single letter, though.
What do you mean?
Well, The internal computer receives a character code from the PC. It then has to calculate the shortest rotational distance to find that specific character on the wheel.
Oh, right, it has to find the letter first.
Exactly. Then it fires a stepper motor to spin the wheel. That stepper motor has to arrest the momentum of the spinning wheel and stop it on a microscopic dime.
What?
Then the hammer fires. Then the carriage motor has to physically move the entire heavy wheel assembly one space to the right, and then the whole process starts all over again.
Just for the next letter.
Yeah. Doing all of that physical kinetic work 18 times in a single second is actually a minor miracle of mechanical engineering when you think about it.
I just try to put this into a modern context for anyone listening today. Imagine you're sitting at your desk right now, and you need to load a web page for your job.
Yeah.
You have two internet service providers you can choose from. Provider A loads a beautifully rendered, high-resolution web page with flawless typography, but it takes 12 full minutes of sitting there staring at the screen while it loads line by agonizing line.
That sounds like torture.
Right. And Provider B gives you a slightly ugly, compressed, pixelated version of the exact same web page, but it loads in 2 seconds. Would anyone today make that trade? Would anyone choose the 12-minute wait for aesthetic perfection?
In our hyper-accelerated digital world where we abandon a video if it buffers for more than, 3 seconds, almost certainly not.
Definitely not.
We prioritize instant gratification above almost all else. But in 1984, people gladly accepted the wait, and they gladly paid £1,500 in today's money for the privilege. It really proves how vital professional appearance was. You were literally buying corporate prestige.
So you've spent your £1,500, you've accepted your 12-minute wait for a 2,000-word article, and you bring this aesthetic perfection home. But you have to actually put it somewhere.
Yeah, finding space was an issue.
And the physical presence of this machine, the footprint, the weight, the sensory impact, is a whole other reality we have to explore. Because this thing was a behemoth.
It was a massive physical commitment of desk real estate. The dimensions listed in the review put the Juki 6100 at 20.5 inches wide, 5.9 inches tall, and 14.2 inches deep.
That is enormous. That's almost 2 feet wide.
Yeah.
The reviewer notes it's about 6 inches wider and 2 inches deeper than the Epson dot matrix.
It took over the desk.
You couldn't just tuck this onto a small side table or hide it on a bookshelf. It demanded a massive chunk of your primary workspace. It was the centerpiece of the room, whether you wanted it to be or not.
And yet, within the context of 1984, the reviewer actually praises its size. By the standards of its own Daisywheel class, the Juki was considered relatively compact.
Really?
Yeah. But the truly crazy metric here isn't the dimensions, it's the mass.
Yes. The weight. The raw specs list the Juki 6100 at 27 pounds.
27 pounds.
Let that sink in. 27 pounds. That is the weight of a gold bar. It's the weight of a healthy 2-year-old toddler.
It's heavy.
Why on earth did a printer need to weigh 27 pounds? Was it just covered in thick metal casing or something?
Actually, the external casing was injection molded plastic. The weight came from the sheer heavy-duty mechanics required to execute that 18-character-per-second dance we talked about.
Oh, all those motors.
Exactly. You have multiple heavy copper-wound stepper motors. You have a solid metal chassis to prevent the machine from literally warping under its own internal forces.
Yeah.
You have a heavy rubber platen, that's the roller that feeds the paper, and the print carriage itself, which houses the wheel and the hammer, is a dense block of metal that has to be thrown back and forth across the page.
But the most hilarious part of the review is that 27 pounds is presented as a triumph of lightweight engineering.
I know.
The reviewer explicitly states that it weighs, quote, about 10 pounds less than much of the competition.
It's a fantastic shifting of baselines. The standard competing Daisywheel printers from companies like Diablo or Quame weighed close to 40 pounds.
40 pounds.
They were practically industrial machinery.
There's a great quote in the text about this. The reviewer writes that because the Juki is only 27 pounds, nor will you need to weld bracing struts to the furniture before putting your new toy online.
It reads like a joke, but it highlights a very real, very physical problem of early computing. Those older 40-pound daisy wheels were an absolute nightmare for office furniture.
How so?
Well, when the carriage reached the end of a line, it had to perform a carriage return. That means throwing that heavy block of metal all the way back to the left margin in a fraction of a second.
Oh, I see.
The kinetic force of that sudden stop was violent. If you put a heavy daisy wheel on a cheap, flimsy desk, the sheer rotational torque and kinetic energy would literally threaten to shake the desk apart over time.
He actually says the older models threatened to shake the house down when they burst into staccato action.
It's vivid imagery.
So you're paying top dollar for a machine, and the main selling point is that its relatively, quote, low weight of the moving parts keeps vibration at acceptable levels. You're buying it so it doesn't destroy your desk through sheer kinetic violence.
It speaks to the thoughtful engineering of the Juki, really. The engineers knew they had to tame the beast. And you see that in the physical layout, too. They included little tactile luxuries. For example, the reviewer's thrilled that it features 2 Playton knobs.
Right, I saw that and had to laugh. A knob on the left and a knob on the right. Why was that a feature worth putting in a magazine review?
Think about the ergonomics of loading single sheets of expensive corporate letterhead. You don't have an automated paper tray like we do today.
You have to feed it manually.
Exactly.
Yeah.
You are manually inserting a piece of paper, pulling the Playton knob to feed it through, and painstakingly lining up the top edge so your text prints perfectly straight.
That sounds tedious.
It was. Now, if you only have a knob on the right side and you are left-handed, or if your desk setup forces you to sit slightly to the left, it's a constant, awkward reach. Giving the user a knob on both sides was a tiny, purely mechanical recognition of human comfort.
That's actually pretty thoughtful. But, no amount of ergonomic knobs could hide the fact that this machine was fundamentally a noise factory.
Very true.
The physical noise of the printer was one kind of friction that you just couldn't ignore.
We have to dedicate some time to the acoustics here because sound was a physical presence in the 1984 office. The reviewer calls the noise the Achilles heel of the Daisywheel Printer.
You had these massive mechanical devices operating inches away from where people were trying to think, write, and conduct phone calls. The acoustic profile of your hardware was a major factor in your quality of life.
The text paints an incredibly vivid auditory picture, comparing the dot matrix to the Daisywheel. Let's look at the Epson FX80 first. The reviewer describes its sound as a predictable scream. From a physics standpoint, that makes perfect sense. You have those tiny metal pins firing hundreds of times a second. That high-frequency vibration produces a very high-pitched whining tone.
Ugh, I could almost hear it.
And because the print head moves smoothly and continuously across the page at a constant speed, the tone never changes. It is a continuous, unbroken, high-pitched siren, just an "aye" sound.
A predictable scream. It sounds absolutely nerve-wracking. Now, contrast that with the 27-pound Juki 6100. The text describes it as having an irregular beat and a staccato action.
This goes back to the stepper motors we discussed. The Daisywheel's timing is entirely dependent on the data it's printing.
What does that mean for the sound?
Well, if it needs to print the word VHE, and the letters TH80 happen to be located right next to each other on the physical wheel, the machine can spin the wheel tiny distances and fire the hammer rapidly. Thwack, thwack, thwack.
Okay.
But if the next word requires a letter on the complete opposite side of the wheel, the motor has to spin it 180 degrees. That takes an extra microsecond.
So the rhythm is constantly breaking. It's not a smooth whine. It's a halting, unpredictable machine gun stutter. Thwack, 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 thwack. Like a tiny, erratic percussion instrument hammering into your desk. And remember, because it's so slow, this irregular thwacking goes on for 12 straight minutes.
It sounds like psychological torture. And yet, the crucial insight from the review is that the reviewer found the Juki's 12-minute stutter subjectively less irritating than the Epson's 2.5-minute scream.
That feels completely counterintuitive.
Yeah.
How is 12 minutes of a machine gun better than 2 minutes of a whine?
It comes down to psychoacoustics. The Juki was much lower pitched. You have a heavy, solid plastic wheel being struck by a metal hammer against a thick rubber roller. It creates a thud, a heavy clatter, rather than a piercing shriek.
That makes sense.
The human nervous system is generally much more fatigued by sustained high-frequency noise. A high-pitched scream triggers a biological stress response. It sounds like an alarm. The low-pitched, heavy thudding of the Juki, even with its irregular beat, fades into the background noise of an office much more easily. It sounds like physical labor. It sounds like work being done.
Plus, the engineers at Juki actively tried to dampen it. The review notes that the translucent plastic dust cover over the print mechanism wasn't just there to keep out cigarette ash and coffee spills. It actively functioned as an acoustic muffler.
Exactly.
You pull the lid down, and the machine gun fire gets slightly muffled. It's just wild to picture people sitting in a smoky 1980s office trying to concentrate on a spreadsheet, while this 27-pound plastic box violently thwacks out a report right next to their elbow.
It underscores how tactile the computing experience was. You felt the vibration in your desk, you had the mechanical labor, you smelled the ink.
The physical presence, the weight, the noise, it demanded your attention. But the hardware itself demanded your interaction in ways that seem completely alien today. Which brings us to the operational experience.
Yes, the hands-on part.
In 1984, an immense amount of technical responsibility was placed squarely on the consumer's shoulders. The invisible friction of getting the computer to actually talk to the printer was arguably much louder than the mechanical thwacking.
We are so spoiled today. We expect total plug-and-play capability. You plug in a USB cable, the operating system shakes hands with the device, downloads a driver invisibly from the cloud, and you're ready to print.
It's completely thoughtless now.
But the Juki 6100 existed in a universe where the concept of a universal operating system driver barely existed.
It was an era of total user empowerment. You had the power to configure everything, but that empowerment came with a steep learning curve and some truly bizarre quirks.
Let's talk about those quirks.
Let's start with one of the most visible ones, right on the front panel of the machine, the pitch slider. The reviewer calls this an immediate attention grabber. It's a physical sliding switch that lets you control the pitch, meaning how many characters fit into an inch of paper. You could slide it to 10 pitch, 12 pitch, or 15 pitch.
From a purely visual UI perspective, this is a brilliant piece of design. Normally, in 1984, if you wanted to change the character spacing, you had to embed complex, obscure hexadecimal escape codes into your word processing software, hoping the printer understood them.
Which sounds awful.
Or you had to dig into the back of the machine and flip tiny microscopic toggles. Juki brought that control right to the surface. A big, friendly, tactile slider. You want smaller text? Slide it to the right.
I thought it was brilliant too until I read the fine print in the review. The implementation is hilariously flawed by modern standards. The reviewer explicitly points out that you can't, in his words, change horses in midstream.
Ah, yes. The reboot requirement.
Let's see if I have this right. Printing a document, I look at the page and realize, oh, the text is too big, it's spilling over the margins. I can't just reach over and move the slider to 12 pitch and have the printer instantly adjust on the next line.
Absolutely not. If you touch that slider while the machine is on, nothing happens. To make the printer recognize the new pitch setting, you have to literally reach around to the back, flip the heavy power switch to O-off-F, wait a few seconds for the capacitors to drain, and turn the entire printer back on again.
That is absurd. It's like having a car where if you want to turn on the windshield wipers, you have to pull over to the side of the highway, turn the engine completely off, flip the wiper switch, and restart the car.
It's a great analogy.
Why design a physical slider if the machine can't react to it in real time?
It perfectly illustrates the severe limitations of hardware memory and processing at the time. A printer today has more processing power than the Apollo moonlander, constantly monitoring sensors and inputs. The Juki 6100 had a tiny, primitive logic board.
So it couldn't handle the multitasking.
Right. It did not have the processing overhead to constantly pull the position of that physical slider while also doing the complex math required to spin the daisy wheel.
So it only checked the slider once.
Exactly. During the boot sequence, when you flip the power on, the logic board runs a diagnostic. It checks the physical position of that switch, reads the electrical resistance, locks that value into its tiny bit of memory, and sets the mechanical timing gears for the carriage motor accordingly.
And then it just ignores it.
Once the boot sequence is over, the printer stops looking at the switch entirely. To change the mechanical timing, you have to force the machine to completely dump its memory and start the boot sequence over from scratch.
It's a massive quirk.
Yeah.
But if we want to talk about user empowerment, we really have to look under the hood, or literally under the top cover, because the true magic of the Juki's design was its accessibility.
Yes.
The review praises this heavily. He says, quote, "One of the most inconvenient aspects of many printers is gaining access to the DIP switches, but the Juki is definitely superior in this respect." Let's explain DIP switches, because that's a term that has largely vanished from the consumer lexicon.
DIP stands for Dual Inline Package. Essentially, they are a tiny row of microscopic toggles, little plastic switches, mounted directly onto the main green circuit board of a device.
Okay.
Because operating systems like MS-DOS didn't have universal software drivers to tell the hardware how to behave, you had to physically configure the hardware's deepest foundational settings manually before any software got involved.
Right. And on most printers of the era, this was a total nightmare. The manufacturer would hide the DIP switches. You'd have to unplug the machine, flip this 40-pound beast over, unscrew a metal shielding plate, maybe remove the paper feed mechanism, and use a tiny jeweler's screwdriver to poke at these fragile switches deep in the dark bowels of the machine.
But Juki took a totally different approach. The reviewer writes, all you have to do is pull off the top part of the case, and a single bank of switches is revealed, no screws to undo, no need to remove the ribbon nor the paper.
It's beautiful. It shows a level of trust in the user that is completely extinct today. They designed the machine fully expecting, even encouraging, the everyday user to reach in and tinker with the live circuit board.
It's wild to think about.
Though the reviewer does add a very British cautious warning. It is, however, a good idea to switch off the power before you get stuck in.
A highly advisable warning when you are reaching your fleshy fingers down toward an exposed logic board sitting next to a high-voltage power supply.
Definitely.
But let's break down what these tiny switches actually accomplish, because it shows how incredibly customizable this machine was on a physical level.
Okay, there are 9 switches in this main bank. Switch 1 determines if a carriage return automatically implies a line feed, which means when the carriage slams back to the left margin, should it automatically roll the rubber plating up to start a new line, or should it wait for a separate command?
Switches 4, 5, and 6 are used in combination. By flipping them in different binary patterns, you tell the printer's brain which of 8 different international character sets to expect from the computer.
Switch 7 tells the printer if you are feeding it one single sheet of paper at a time, or if you are using a continuous perforated roll of stationery.
But the most fascinating ones, and the ones that really highlight the mechanical reality of the era, are switches 2 and 3. Switch 2 is purely mechanical in its outcome. It selects one of 2 levels of Daisywheel impact intensity.
I saw this and immediately formulated a hypothesis.
Yeah.
I figured, okay, this thing sounds like a machine gun. Switch 2 must be a volume control. You flip it to lower the intensity, the hammer strikes softer, and the machine gets quieter. But that doesn't make sense mechanically, does it? If you strike the wheel softer, the ink won't transfer.
You're half right. It does make it slightly quieter, and more importantly, the lower intensity setting reduces the physical wear and tear on the plastic Daisywheel pedals.
To save the plastic.
Right. Those tiny plastic stems were fragile. If you hammered them at maximum force for hundreds of thousands of characters, they would eventually fatigue and snap off, and you'd have to buy a new wheel. So for normal daily printing, you absolutely wanted the lower intensity setting to save your hardware.
But then why offer a high-intensity mode at all?
Because of the reality of the 1980s office carbon copies.
Oh.
Yeah. If you were a logistics company printing a shipping manifest or an accountant printing an invoice, you didn't just print one copy. You used multi-part forms. You had a top sheet of thin paper, a layer of carbon paper beneath it, another sheet of paper, more carbon, and a bottom sheet, sometimes 3 or 4 layers deep.
And a delicate hardware saving tap isn't going to push the physical force through 4 layers of paper and carbon.
Exactly. The standard hammer strike would leave the bottom copy completely blank. So you pop the lid off, reach your fingers in, flip switch 2, and literally crank the physical violence of the machine up to maximum.
That's amazing.
The internal electromagnet is given a larger jolt of power. The hammer flies forward with increased velocity and forcefully smashes that plastic wheel through, as the reviewer perfectly describes it, weighty wads of carbon paper.
It is visceral engineering. You are physically tuning the kinetic violence of the machine to suit the density of your stationery. That is incredible.
It gives the user absolute control over the trade-off between hardware longevity and immediate practical output. And then we have Switch 3, which introduces us to what might be the ultimate 1980s tech headache, the IBM PC diplomatic crisis.
Oh, man. The IBM personal computer. This was the undisputed heavyweight champion of the corporate desk. It was the standard. You would naturally assume that plugging a printer into an IBM PC would be the most reliable, thoroughly tested interaction in the world.
You would assume that. But the 1980s hardware landscape was like the Wild West. There were theoretical standards, particularly the Centronics parallel port standard for printers, but every manufacturer interpreted the electrical timing slightly differently.
So it wasn't really a standard at all.
Not perfectly. And the IBM PC had a very specific, highly impatient idiosyncrasy when it came to sending data.
The reviewer calls it a habit of cutting off diplomatic relations with any peripheral that hasn't heard from for a while. I need an analogy for this because the technical mechanics are dense.
Think of it like a dictation scenario. Imagine the IBM PC is a hyperactive, incredibly fast-talking corporate boss who is reading a 10-page document out loud. The Juki printer is the secretary trying to type down every word.
Okay, I'm with you. Boss and secretary.
The problem is the secretary, the Juki, has a very short-term memory. In technical terms, it has a tiny internal memory buffer of only 2 kilobytes. That's enough to hold maybe one single page of text at a time.
Not a lot of room.
No. So the boss starts shouting the document at lightning speed. Within a fraction of a second, the secretary's 2K memory is completely full.
So the secretary has to yell, "Stop, hold on, let me type this page out."
Exactly. The Juki sends an electrical signal back down the parallel cable saying, "Buffer full, pause transmission." Now, a normal patient computer would just stand there holding the rest of the document, waiting for the printer to say, "Okay, my buffer is empty, send the next page."
Like a normal conversation.
But the IBM PC was the worst kind of boss. It was incredibly impatient. If the printer didn't ask for more data within a strictly defined, hard-coded timeout period, the IBM PC wouldn't just wait. It would assume the printer had died or been unplugged or caught fire.
It'd just fire the secretary and walk out of the room. It would close the communication channel entirely.
Yes. And because the Juki is so painfully slow stuttering along at 18 characters a second, it takes a very long time to type out that single page of memory. Long enough that the IBM PC's internal stopwatch runs out, triggers its timeout protocol, drops the parallel port connection, and throws an error on the screen.
What a disaster.
So 12 minutes later, the Juki finishes its single page, looks up and says, "Okay, send page 2." And the IBM PC has completely hung up the phone. The print job is dead.
It is a catastrophic breakdown in communication between the two most expensive pieces of equipment on your desk. So how did users actually fix this? You can't just download a patch from the internet. This is where the manual for the Juki 6100 reaches legendary mythical status in my mind.
The Juki manual doesn't just offer an apology. It provides a deeply technical, profoundly user-empowering solution. First, you flip that DIP switch 3 to AW-N, which slightly alters how the Juki's buffer handles the electrical handshake signal.
Okay, simple enough.
But for some high-end software running on the IBM PC, even tweaking the hardware switch wasn't enough to stop the PC from timing out.
Right. The manual goes a step further. It tells the user to fix the problem by manually modifying the raw machine code of their word processor itself. And not just any word processor, it specifically targets WordStar, which was one of the most popular, most expensive professional software packages on the market at the time.
Think about the sheer audacity of this from a modern perspective. The manual for a 370-pound budget printer tells the end user to boot up MS-DOS, launch a low-level system utility called debug.com, and open up the commercial wordstar.com executable file.
Explain what debug.com is, because this is wild.
Debug.com was a command line tool designed for programmers. It allowed you to view and directly alter the raw hexadecimal machine code of a program. It bypasses the operating system entirely. You aren't changing settings in a menu. You are fundamentally altering the compiled DNA of the software.
I am just picturing a regular office worker, an accountant, or an administrative assistant with no computer science background, following a printer manual's instructions to open up their wildly expensive WordStar program in a hex editor. The manual literally tells them, go to memory address 0A4B and change the hex value 7F to FF.
Let's translate that into plain English because it's a beautiful piece of hacking. Memory address 0A4B is simply the exact physical location on the floppy disk where the programmers at WordStar stored the value for the printer timeout limit.
And what do those numbers 7F and FF actually mean?
They are hexadecimal values, which is a base 16 counting system computers use to represent binary data compactly. A standard byte of data is 8 bits. The value 7F in hexadecimal translates to 011111 in binary, or the number 127 in decimal.
Okay, so 127.
So the WordStar software was hard-coded to wait for 127 units of time, likely milliseconds or processor ticks, before giving up on the printer.
But 127 units isn't nearly long enough for the slow Juki to empty its buffer.
Exactly. So the manual tells you to delete the 7F and type in FF. FF is 11111111 in binary. It is the number 255 in decimal. It is the absolute maximum value you can cram into a single 8-bit byte of memory.
Oh, I see.
By making that change, the user is manually rewriting the software's timeout threshold, doubling the amount of time the IBM PC will wait before dropping the connection.
They are literally hacking their own commercial software just to make it talk to their printer. It is breathtaking. Today, if an app is a glitch, we are completely powerless. We sit there and wait weeks for the developer to push an automatic update over the cloud, assuming they ever do.
If we're lucky.
Right. In 1984, the hardware manufacturer handed you a digital scalpel, pointed to the screen, and said, "Here is the exact byte of code causing the bottleneck. Go in there and cut it out yourself." It assumes a level of technical competence and bravery that is almost entirely extinct in the consumer market today.
It's terrifying, certainly. If you make a typo in debug.com and change the wrong memory address, you could irreversibly corrupt your entire word processing system.
You'd break the whole thing.
But it's also incredibly liberating. You owned the machine, you owned the software, and you had the unfettered power to make them bend to your will.
So you've hacked your software, you've flipped your DIP switches, the PC is waiting patiently, and the printer is finally thwacking away.
Yeah.
But your work still isn't done. Because a mechanical beast like this constantly needs to be fed.
Yes, the consumables.
The hardware setup was just the beginning. Keeping it running was an ongoing battle. Let's talk about the consumable ecosystem.
Right. A Daisywheel printer isn't a set-it-and-forget-it device. It requires a constant stream of raw materials to function, primarily the daisy wheels themselves and the ribbons. And the economics of those consumables dictated how you worked.
Let's focus on the ribbon dilemma because it highlights how delightfully analog and physical this process was. The Juki 6100 didn't invent a new proprietary ink cartridge. It used ribbons that were mechanically identical to those used by the legendary IBM Selectric typewriter.
Which was a very smart move.
And when a user walked into an office supply store, they basically had two mutually exclusive choices: the single-pass carbon ribbon or the multi-strike cloth ribbon.
This is a classic 1980s example of having to balance absolute quality against pure economics. Let's look at the mechanics of the single-pass carbon ribbon first. It was exactly what it sounds like. It wasn't cloth, it was a spool of very thin, delicate mylar plastic film. One side of this film was coated with a layer of dry, powdery carbon ink.
So when the mechanical hammer strikes the plastic daisy wheel pedal against the ribbon, what exactly happens at the point of impact?
The immense physical pressure of the pedal literally shears that exact shape of dry carbon completely off the plastic film and fuses it directly onto the paper fibers.
Which means the visual output must be stunning.
It was peerless. Because you are transferring a solid block of dry carbon, the edges of the letters were razor sharp. There was no bleeding into the paper. The black was incredibly deep and opaque. It looked like professional high-end typesetting.
However, because it physically removed the carbon from the plastic, there is a massive drawback. You literally leave a transparent window in the shape of a letter E or A on the ribbon.
Right, like a stencil.
You can't hit that exact spot on the ribbon ever again because there's no ink left. If you hit it again, the hammer just strikes clear plastic and nothing prints on the page.
Exactly. The machine has to constantly, aggressively wind the ribbon forward to completely fresh, untouched territory for every single piece stroke. It eats through the spool at an alarming rate.
Now, the review notes that the Juki 6100 was actually very clever about maximizing the lifespan of these carbon ribbons. It didn't just strike the middle of the ribbon and waste the top and bottom edges. The reviewer praises the mechanism, saying it does a, quote, very good job at squeezing the most out of its ribbons, striking each bit of the ribbon in 3 vertically arranged tracks.
Yes, the print carriage would physically shift the ribbon cartridge up and down a few millimeters. It would print a letter on the top third of the ribbon, advance it slightly, print a letter on the middle third, advance it, and print on the bottom third. It utilized almost the entire surface area of the expensive carbon film.
Even with that ingenious 3-track efficiency, the lifespan is incredibly short. The reviewer calculates that a single-pass carbon ribbon only lasted for about 160,000 characters.
Which isn't much.
Translated into human terms, that's roughly 27,000 words. If you are an author writing a novel or a busy legal office printing thick contracts, you're going to burn through an entire ribbon every couple of days.
Which is an expensive proposition. And that brings us to the alternative, the multi-strike cloth ribbon.
How does the physics of the cloth ribbon differ from the carbon film?
Instead of dry carbon powder on plastic, you have a tightly woven fabric ribbon that is deeply saturated in wet liquid ink. When the hammer strikes the pedal against the cloth, it acts like a sponge. The pressure squeezes the wet ink out of the weave and onto the paper.
But here's the magic trick of the cloth ribbon capillary action.
Yes.
Because the ink is wet and the cloth is a woven matrix, once the hammer lifts off, ink from the surrounding unstruck areas of the ribbon slowly seeps back into the dry spot to replenish it.
Precisely. Capillary action draws the ink back, so you could strike the exact same piece of ribbon over and over and over again. The printer didn't have to wind the spool nearly as fast. The reviewer calculates these cloth ribbons were good for at least 100,000 words. That's almost 4 times the lifespan of the expensive carbon ribbon.
But you sacrifice the aesthetic perfection. Because as wet ink on cloth, the impact diffuses slightly. The edges of the letters aren't as razor sharp. And more importantly, the output quality degrades slowly over time.
It's the progressive fade. The advantage of the cloth ribbon isn't just that it's cheaper to run, it's how it fails. With a cloth ribbon, the print just slowly gets fainter, lighter, and grayer over tens of thousands of words.
You get a warning.
Right. You have days or even weeks of visual warning that the ink is drying up and it's time to go to the store.
Which brings us to one of the most evocative, stress-inducing parts of the magazine review. The reviewer outlines a highly specific scenario that highlights the absolute terror of choosing the high-quality carbon ribbon. I want to address you, the listener, directly here, because this scenario is the ultimate distillation of 1980s analog anxiety.
It really is a nightmare scenario.
Picture this. It is 11:00 p.m. on a Sunday night. You have a massive 12-page financial report that is absolutely critical. It has to be sitting on your boss's desk or your biggest client's desk by 9:00 a.m. on Monday morning. You are printing it out on your massive Juki 6100, and because it's an important document, you're using a beautiful, crisp, single-pass carbon ribbon. You're on page 9. The machine is thwacking away in the quiet house, and suddenly, snap.
The spool runs out of fresh film. Or worse, the fragile plastic mylar tears under the force of a heavy hammer strike.
And you are completely dead in the water. It is 11:00 p.m. on Sunday in 1984. There are no 24-hour mega office supply stores. Amazon Prime does not exist. You cannot just export a PDF and email it to your boss.
No, you cannot.
The physical piece of paper is the only acceptable output. If you do not have a backup carbon ribbon sitting in your desk drawer, your project has failed. You're going to miss the Monday morning deadline, lose the account, or fail the class purely because you ran out of a spool of plastic film.
It perfectly illustrates the intense physical stakes of analog workflows. The reviewer points out that if you were using a cloth ribbon in that exact same Sunday night scenario, even if it was at the absolute end of its life, you could, in his words, always squeeze a few more pages of print out of it, even if the quality isn't everything you might have hoped for.
You'd at least have something to hand in.
The cloth ribbon would give you a faded, gray, barely readable page 12, but it would give you a page 12. You could hand something in. The carbon ribbon gives you nothing. It is a catastrophic, binary failure state.
The Sunday night panic. It's a real visceral fear that completely vanished once we shifted to digital delivery. But the fact that the Juki gave you the choice, that its physical carriage was engineered to seamlessly accommodate both the IBM-style carbon spools and the cloth spools, points to one of its greatest underlying strengths. We need to talk about cross-compatibility as a deliberate design feature.
This is a crucial area of analysis because it contrasts so sharply with the business models of today. In the early days of computing, many hardware manufacturers aggressively tried to lock users into proprietary ecosystems.
Like they do now.
Right. It's a strategy we call vertical integration or proprietary lock-in. They wanted you to buy their expensive printer, use their specific, weirdly shaped cables, buy their proprietary ink cartridges that only fit their machines, and use their custom fonts.
We still see that today.
Yeah.
Try putting a cheap third-party ink cartridge into a modern Wi-Fi printer and watch the machine throw an absolute fit, refusing to print until you buy the official $60 brand name cartridge.
Exactly. It's a deeply anti-consumer practice. But Juki took the exact opposite approach with the 6100. They didn't try to reinvent the wheel literally or figuratively. They built what is essentially a Frankenstein's monster constructed from the best available open industry standards.
Let's list the standards they adopted because it's impressive. First, the command codes. The invisible software signals from the PC that tell the printer to underline a word or bold it or print a superscript numeral. Juki programmed their logic board to be entirely identical to the Diablo 630 standard.
The Diablo 630 was a massive, incredibly expensive, industry-standard commercial printer. It was the gold standard. By adopting the Diablo codes, Juki ensured that literally any word processing software that knew how to talk to a high-end Diablo could instantly, flawlessly talk to the budget Juki. You didn't need special drivers.
Then there are the ribbons, which we just discussed. They didn't invent a weirdly shaped Juki ribbon cartridge. They designed the carriage to accept ribbons identical to the IBM Selectric typewriter. Why is that important? Because every single office supply store in the world, every corner stationery shop, had a wall dedicated to IBM Selectric ribbons. You would never, ever struggle to find ink.
And finally, the daisy wheels themselves. They didn't invent a proprietary patented Juki font wheel. They designed the print head hammer and alignment gears to accept off-the-shelf wheels that were compatible with Triumph Adler machines.
So you had this massive pre-existing global library of fonts and typefaces available to you from day one. You could go buy cheap plastic Triumph Adler wheels for everyday draft use, or you could invest in heavy-duty, expensive metal wheels for high-volume corporate workloads.
By embracing these varied standards, Diablo for software, IBM for ink, Triumph Adler for fonts Juki ensured that their users would never be orphaned. If the Juki Corporation went completely out of business the day after you bought the printer, it wouldn't matter. You could still get ribbons, you could still get replacement wheels, and your software would still know how to drive it. It was a profoundly pro-consumer design philosophy that respected the user's investment.
Which brings up a fascinating logistical question. If you are a consumer in 1984 and you bring home this Frankenstein's monster of a machine, how do you actually learn to navigate all this?
Yeah.
How does a normal person learn about Diablo codes, Triumph Adler wheels, capillary action, hexadecimal hex editing hacks in debug.com, and the IBM parallel port timeout limits? You couldn't just Google Juki 6100 setup tutorial or watch a YouTube video.
You relied entirely on a piece of literature that is practically extinct in the modern world, the high-quality technical manual.
I genuinely mourn the loss of the technical manual. Today, you open a $1,000 piece of hardware and you get a single, flimsy piece of paper with 3 confusing pictograms showing you how to plug it into the wall and a QR code that links to a generic, unhelpful support website.
But the manual for the Juki 6100 was a different breed. The reviewer, Simon Craven, dedicates an entire glowing section of his magazine review just to praising the physical book that came in the box. He calls the documentation of unusually high quality and says it's a powerful incentive for selecting this product over some of the alternatives. He actually writes the sentence, "In an ideal world, all computers, software, and peripherals would come with a manual this good."
What made it so exceptional, it wasn't just a dry list of specifications, it respected the reader's time. The reviewer notes it had a clear, well-designed contents page and, crucially, a decent index.
A feature noticeable by its absence on too many computer products, the reviewer Riley notes. The fact that a tech journalist has to explicitly praise the mere existence of an index tells you how abysmally bad the industry standards for documentation were in 1984.
But it wasn't just reference material, it was engaging to read. The review notes the manual was beautifully written with a noticeable American idiom which manages not to get in the way of the information.
And it had cartoons.
Yes. It actually featured numerous illustrated cartoons scattered throughout the text. The reviewer says they injected a little levity into what could too easily become a dull subject. Can you imagine a modern, sleek corporate entity like Apple or Samsung, including humorous, hand-drawn cartoons in their packaging to lighten your mood while you figure out why your device won't connect to the Wi-Fi? It's charmingly human.
It is human. But, more importantly, a manual is only as good as its technical scope. And the scope of the Juki 6100 manual was breathtaking. It didn't just tell you how the printer worked in a vacuum. The authors recognized a fundamental truth. A printer is only useful when connected to a larger ecosystem.
Right. They didn't just say, here are our specs, good luck hooking it up.
Yeah.
The manual had specific, dedicated, highly detailed chapters on how to interface the Juki with the most popular personal computers of the era. It had a chapter for the IBM PC, a chapter for the Apple II family, the K-Pro, the Osborne 1 Portable, the TRS-80 Model 3.
We need to pause and appreciate what an incredible undertaking that was by the technical writers. Today, a peripheral basically just needs to work with Windows and macOS. The architectures are standardized. But in 1984, an Apple II, an Osborne 1, and an IBM PC were entirely different alien ecosystems.
Completely different languages, basically.
They handled data differently, they wired their ports differently, their operating systems were completely unique. The writers at Juki had to research, acquire, and physically test the printer against half a dozen entirely different hardware architectures, map out the quirks of each, and then write clear step-by-step connection guides for the user of each specific machine.
And they went even further than the hardware. They included software guides, specific instructions for configuring WordStar, Perfect Writer, and Superscript for the Tandy computers. They held your hand through the entire integration process, right down to explaining those hexadecimal hacks we talked about earlier.
It reflects a corporate philosophy that the manufacturer's responsibility doesn't miraculously end at the physical edge of their own hardware. They understood that the user's goal wasn't to operate a Juki 6100 printer. The user's goal was to successfully print a legal contract from an Apple II computer using WordStar software. And the manual was painstakingly designed to facilitate that ultimate real-world goal.
It's just a beautiful artifact of a bygone era of customer care. And the manual also detailed the physical expandability of the machine. You weren't just stuck with the base model you bought on day one.
No, it was modular. It was designed to grow with your needs. If you were a business and you were tired of a secretary having to manually feed single sheets of letterhead into the platen every 12 minutes, you could buy an optional continuous stationary tractor feed device.
That's industrial.
It was a mechanical assembly that bolted directly onto the top of the printer. It had sprockets that grabbed the holes on the sides of continuous paper rolls and fed it perfectly straight. It even featured an accompanying end-of-paper detector wired into the logic board so the printer wouldn't just blindly keep hammering the ink ribbon into the bare rubber platen when the paper roll eventually ran out.
But my absolute favorite upgrade, the one that truly shows how different the era was the memory expansion. We talked earlier about that tiny, bottlenecked 2-kilobyte memory buffer that caused the IBM PC to hang up in frustration. If you wanted to fix that, you didn't have to buy a completely new upgraded printer.
No, you just upgraded the brain yourself.
You literally went to an electronics catalog, bought standard 2K static RAM microchips, popped the top cover off the printer, located the empty sockets on the green circuit board, and physically pushed the raw silicon chips into the board to boost the buffer up to 8 kilobytes. And the manual, of course, had full illustrated fitting instructions and a list of compatible memory chips. You were executing motherboard upgrades on your printer at your own desk.
It's a level of modularity and repairability that the modern right-to-repair movement is only just starting to beg legislators to mandate again today. We had it in 1984 and we gave it away.
But before we wrap up, we have to touch on the final piece of the magazine review, because the reviewer includes a postscript that provides a fascinating, somewhat tragic counterpoint to everything we've praised about the 6100.
Ah, yes. The disappointing successor, the Juki 6300.
At the very end of the article, the reviewer briefly evaluates the newly released Juki 6300. This was marketed as the bigger, heavier, more expensive professional sibling to our 370-pound budget hero. On paper, it should be vastly superior. It had a much wider carriage so it could print sideways on massive corporate accounting ledgers. And it featured a significantly higher speed, though the review doesn't give the exact characters per second metric. It was a solid, heavily engineered machine.
But the reviewer strikes a melancholy tone. He notes that the new 6300, nevertheless, lacks some of the 6100's thoughtful touches.
This broke my heart to read. What exactly did they remove to make it more professional?
They removed the humanity from the design. Remember that fantastic, immediate, attention-grabbing physical slider on the front panel? The one that let the user instantly slide between 10, 12, or 15 pitch spacing.
The one you had to reboot the printer to use, but it was right there, proudly on the front dashboard.
Gone. On the expensive professional 6300 model, that tactile external control was completely removed. It was replaced by a complex combination of tiny internal DIP switches. If you wanted to change the font spacing, you had to stop what you were doing, open the chassis, and dive back under the hood with a screwdriver.
Oh, that's such a downgrade. And the type scales. The little rulers physically engraved into the plastic dust cover, which helped the user manually align their paper perfectly before printing.
Omitted entirely on the new model. The plastic cover was just smooth, featureless plastic.
Why would they do that? Did the engineers just get lazy?
No, it wasn't laziness. It was a deliberate shift in target demographics. It's a classic technology story. The 6100 was built thoughtfully for the everyday amateur user. It was for the small business owner or the home enthusiast who needed physical help aligning paper, who wanted a big, friendly slider to understand what the machine was doing, and who needed a friendly manual with cartoons.
Yeah.
The 6300, however, was built for the corporate typing pool.
Ah, I see.
In a massive corporate typing pool, the user isn't supposed to change the settings. The IT technician sets the DIP switches once, locks the machine, and the secretary just feeds paper into it all day. The user isn't empowered, they are just an operator. The 6100 had soul because it was built for a human. The 6300 was built to be a faceless corporate appliance.
Sometimes the budget model, the slower model, is the true design masterpiece because it has to try harder to win you over. Which brings us perfectly to the conclusion of our deep dive today. So, taking all of this in the mechanical violence, the hacking, the ribbons, the costs, what is the final verdict on the Juki 6100?
Objectively, by any modern metric, the Juki 6100 was a nightmare. 18 characters a second is agonizingly slow. It was loud, filling the room with staccato machine gun fire. It was incredibly heavy, a 27-pound block of plastic and metal dominating your desk, and it required you to hack your own software just to make it work.
All true.
But despite all of those immense flaws, it was a masterpiece of its era. It was a hyper-compatible, highly modular, user-serviceable workhorse. It offered staggering value for money, bringing elite professional typewriter quality to the budget consumer market. And above all else, its design, its manual, and its open architecture treated the user with profound, unyielding respect.
It's a stark, almost painful contrast to where we are today. I want you, the listener, to pause and look around your desk or your workspace right now. Look at your smartphone. Look at your ultra-thin laptop. We are surrounded by sleek, silent, lightning-fast devices. They are magical, but they are also sealed shut with proprietary pentalobe screws and industrial-strength adhesive. We have gained immense, unbelievable convenience over the last 40 years, but we have traded away our ownership to get it.
We traded ownership, modularity, and repairability for sleekness and speed. We no longer possess a tactile, physical understanding of our tools. We don't tune the mechanical impact hammer to match the thickness of our carbon paper. We don't upgrade the physical memory banks of our peripherals. We just tap a smooth glass screen and blindly hope that an invisible, corporate-controlled cloud server handles the rest. We are no longer the mechanics of our own digital lives. We have been relegated to the role of mere passengers.
And that brings me back to where we started, that image of the 12-minute wait. The agonizing 12 minutes it took the Juki 6100 to hammer out a 2,000-word article, character by character, thwack by thwack, while you sat there and watched the physical plastic ribbon spool unwind.
It was a serious, non-trivial investment of time and material.
It was. And because it took 12 minutes of loud mechanical hammering, and because you knew that carbon ribbon was expensive and running out, you had to be absolutely 100% sure your words were worth printing. You didn't just casually hit print on a rough draft to see how it looked. You reviewed it on the screen. You proofread it. You perfected it. Because the physical act of manifesting those words into reality had a high cost in time, money, and noise. In our modern age of instant, silent, unlimited digital output, where a 2,000-word document can be generated by AI, duplicated flawlessly, and transmitted to 1 million people in the blink of an eye, has the sheer frictionless speed of creation fundamentally devalued the weight of the words we produce?
That is a profound question. When words are free and instant, do they mean as much as when they cost 12 minutes of mechanical labor? It's definitely something to think about the next time you hit print.
Until next time, keep diving deep.